This is Introduction to Newton's Laws 1. To solve a Newton's second law problem, we need to first choose a system, and then we need to draw all of the forces acting on the object by sketching a free body diagram, which I'm going to abbreviate from now on as just FBD, because it's quicker to write. Then we need to choose a coordinate system, and this is an important point which we will lean on here in the next couple of videos. One of the axes of our coordinate system has to point in the direction of an acceleration. We'll make sure that we see that. And then we want to set up Newton's second law in both directions by writing equations that have the general form. There are any number of ways we could express this. We could say the sum of the forces is equal to the mass times the acceleration. That's one way to say it. You could say F net is equal to the mass times the acceleration. Some teachers prefer to write it in terms of acceleration. Acceleration equals sum of the forces divided by the mass, or the acceleration equals the net force divided by the mass, and that's fine. But for me, it's simpler without any denominators. So that's why I like to write it that way. So what we have here is we have a mass that's sliding down a frictionless surface. We can see that mu sub k is equal to 0 here in the problem. And the angle of incline is theta. It says it's not enough to prevent m from moving downward, but we have a force F that's being applied parallel and directed up the ramp. Trying to slow this mass down, it's unsuccessful at fully doing that, stopping it, but it's directed in that direction. Draw a correct free body diagram. Do not show components. This is an important point. If you are going to take the College Board's National AP Physics exam, you cannot show components on a free body diagram, no matter what your first-year physics teacher might have taught you. We want to make sure that each force vector also originates on the dot. What do we have here? I think we have the weight, mg, which acts straight downward. We have the applied force, which is acting that way. And then we have a normal force that is at right angles to the surface. And then right in there, that isn't a force. I'm just showing that you should have learned in a previous physics class that the angle of incline and the angle between mg and perpendicular to the surface, those are numerically equal. So I'm showing theta in there. And we also want to show a coordinate system in here. And the coordinate system, it says, has to be directed in the same direction as the acceleration. So I'm going to call that the x direction. And I'm directing it this way because we're told that it's moving in this direction. It's sliding down a frictionless surface. Let's derive an expression for the mass's acceleration. Let's sum the forces in the y direction. And that's going to be Fn minus mg cosine theta. And according to Newton's second law, that should equal the mass of the object times the acceleration in the y direction. Now, the acceleration in the y direction is 0. It's not accelerating into the surface or off of the surface, which means that in this case, the normal force is numerically equal to mg cosine theta. Now, let's sum the forces in the x direction. The way it's accelerating down the plane, I like to choose that to be positive. So we're going to have mg sine theta minus f. That is the sum of the forces in the x direction. And that should be numerically equal to the mass times the acceleration in the x direction. Acceleration in the x direction, we're assuming here, is not 0. And we want to derive an expression for this acceleration down the ramp. I think we know everything in this equation except for the acceleration. So I think our final answer here is going to be mg sine theta minus f divided by m. If you want to factor that m out of the first term, you're welcome to do that. So it turns out that this right here, we didn't need it for this problem, but very often we do. In fact, I think the next problem on the next video, we will probably need that, but we didn't need that here. So whenever we derive an expression for something, we need to do so such that everything on the right side of the equation is something that is given to us. And here we are given m. We know what g is. We were given the angle of incline theta. We were given f. So all of this stuff we know, and that gives us confidence that that's going to be the right expression. If you put something in here that is not given to you, then you're going to get some credit taken away for that.